Hi class, Dr. Searcy here with the Chapter 10 Lecture Notes lecture. So first let's note that the title of the chapter is the t-test for two independent samples. The take-home point that you want to get from that title is that we're still talking about this thing that you learned about in Chapter 9, the t-test. We're just going to talk about in Chapter 10 how we could do the t-test a little bit differently than we learned about in Chapter 9. So what do we want to remember from Chapter 9? First, let's just remember that we are talking about conducting a hypothesis test, right? And it had the 4 different steps. Step 1 was where you are stating your 2 different hypotheses, your null hypothesis and your alternative hypothesis. Step 2 is you are finding your critical region, right? You're using your alpha level, number of tails, and your degrees of freedom. You're looking up some t-value in the t-table using those numbers. Then the 3rd step is you're computing your data. You're calculating your data, right? And then that leads to step 4, which is where you decide whether your treatment was effective or not. Remember that the decision is based on, you're asking is the t that you calculated in step 3 bigger than the t that you got in step 2. If the step 3 t is bigger than your step 2 t, then you decide that your treatment was effective. Okay, so with all of that, let's just remember, thinking about that step 3, what was the equation that we had with it? Remember, it was basically this equation here, where you're solving for this t value. Remember the way the equation works is it's like a version of that z equation that we worked with beginning in Chapter 5. The way that the equation works is you've got your numerator, which is your sample mean minus your population mean, and that's divided by your new measure of your standard deviation, this estimate of the standard error of the sample mean. The thing that you want to remember about this was that beginning in Chapter 9, we said that we're using this kind of equation because we no longer know what our standard deviation is, right? Remember, this used to be in your denominator, like back in Chapter 5, and this was in your denominator, like back in Chapter 7. Being in Chapter 9, we said we don't know what these values are anymore, and because of that, we're going to use some other measure of variance. We're going to use the sample variance in place of that, right? So we're saying that the way that we get the estimated standard error is with this formula here, right? The estimated standard error is the square root of the sample variance divided by your n. Big thing that we want to remember from that, though, is, well, how do we get that sample variance? Remember, the way we get that is your sample variance is your sum of squares divided by your degrees of freedom, right? So basically in chapter 9, our step 3 calculation was to first find your sample variance, use that then to find your estimate of the standard error, and use that then to find your t. Okay, so we're more or less going to continue to do that same thing, same idea, but now where we're saying that we're working with these 2 independent samples. So the question with that is, well, what do we mean by these 2 independent samples? We mean that we're using this research design where we are going to recruit 2 different samples, right? 2 different groups of participants, and those 2 samples are going to be independent of each other. They're going to be treated by us differently than we're going to treat each of them. Okay, so we're saying that the researcher is going to collect 2 samples of participants. Where are those 2 samples of participants going to come from? They could come from 2 populations, right? So Maybe we want to compare one population to another population, so we get a sample from one population and then a sample from the other population. Or we could say that we're going to recruit participants, or 2 samples from the same population, but here we're saying if we expose them to two different conditions, we're going to treat those 2 samples differently. Okay, so what are some examples of this? First, let's think of an example with regard to the 2 populations. Right, we could say that an example is, maybe we want to compare the population of men to the population of women and say that they might be affected by something differently. And maybe the thing that we're going to do is go back to that experiment example that we had a couple of chapters ago, where we did the yoga improving classroom behavior. What if we said yoga improves classroom behavior, but maybe it only does it for women, or it only does it for men, right? So we can conduct that kind of experiment. Another kind of experiment that we can conduct is one where we are getting participants from the same population, but like I was saying before, treating them differently. Maybe what we could do is, for one of the samples that we get, we could say that what we're wanting to do is test some kind of new depression medication, right? So we say, okay, we're going to pull 2 samples out of one population of depressed people. One of those samples is going to get the new medication. The other sample is going to get the fake medication. They're going to get the placebo, right? And our goal here is to see, does the level of depression get reduced in either group? What should happen is depression gets reduced here, but depression does not get reduced there, right? And that's what they're going to run this type of experiment to see. Okay, so how do we do it? We basically recruit the participants, we administer the treatment, and then we calculate the data. We collect the data and we calculate it. When we go to calculate it, let's say that, right, we're now in the hypothesis test, and let's say that at this point we are going to run the hypothesis test using the 4 steps, and the first 2 steps are going to go exactly that we've talked about them in previous chapters, right? Step 1, going to do that, the identifying of the 2 hypotheses, the null hypothesis and the alternative hypothesis. That's going to be written exactly the same way that we've talked about it before, so I'm not going to go over it now. Same thing with step 2, the critical region, right? We're still going to find the critical region using the same process that we used in previous chapters. The thing that's going to be different beginning here in chapter 10 is now in step 3, we're no longer using this T formula when we're talking about running it with 2 independent samples. The T formula instead is going to become this T formula. Right, and so I'll explain this real quick. Basically, this T formula is exactly the same formula that you had over here. It's just modified to accommodate the fact that instead of looking at one group, you're now looking at 2 groups. Right, so the way it's modified here is we're still here in this part of the formula, still talking about your sample means, right? That would be this part right here. But now what you're talking about is the difference between the 2 different sample means that you've got in your experiment. Was the one sample mean different from the other sample mean? That difference is then going to be subtracted from the difference of your 2 population means for the 2 samples. By the way, this part of the equation here, the mu1 minus the mu2, this is your null hypothesis statement right here. So what should happen here is this mu1 minus mu2 should equal 0. Let's just keep that in mind when we go to do the actual calculation later. But right now, let's go and move on to the denominator term, right? This is this new type of standard error that we're going to have to find. And this new type of standard error that we're going to find is called the new type of estimated standard error. Before I go to describe this, though, let's kind of leave the whole new T equation with this new understanding. right? Let's think of it as the type of T equation that you conduct, that you'll calculate if you're being told that your samples are independent of each other, right? If they're coming from two different kinds of populations, or it's two different samples where you've done one thing to one sample and something else to another sample. Okay, so how do you get this estimated standard error? Basically, the way that you get it is now with this new equation. What is this new equation? Let me go ahead and describe the whole equation first. Right, we're seeing that it's a square root equation, and underneath the square root is you're adding one fraction to another fraction. What are the parts of the two fractions? Both denominators are the sample sizes of the two samples that you've recruited, right? So this is your sample size of your group 1, and then this is your sample size of your group 2. These two will always be given in the problems that you'll be going to conduct. There is a new term in here that you've never seen before, and that's this term here called the pooled variance. Notice that whatever value you have here, you're going to have the exact same value over here, right? They're exactly the same terms. Okay, so if this is how you get this new estimated standard error, then the new question is, well, how do you get this pooled variance? Before I explain that, let's just first remember that what's happening with the estimated standard error is we're saying that this is where you're combining the error for the two sample means, right? So you're combining the error associated with the first sample and the error associated with the second sample. Okay, so the question that we have to answer right now is, how do we get this thing called pooled variance, right? So remember, pooled variance is this symbol here. The way that we go about getting it is we figure out for our first sample, what was that sample's sum of squares value, and then also for the second sample, what was its sum of squares value. Those two sum of squares value become the numerator of this division problem. We're then finding what were the degrees of freedom for the first sample and what were the degrees of freedom for the second sample. Remember, each one of these degrees of freedom is n minus 1, right? So it's n minus 1 for this and then n minus 2 for that. And that will give you then this division problem that will give you the pooled variance. What is the pooled variance again? Let's just remember it's the weighted mean of the two sample variances, right? Remember, one way that you can remember this is, remember, your S squared is sample variance. So they're just saying, okay, that's sample variance, but pooled, right? Pooled in the sense that it's considering group 1 and group 2. Okay, so from there, before we move on to the next part, we just want to remember, when you go to complete your step 2, right, when you go to find your critical region, remember one thing that you're going to need to have is a number for your degrees of freedom. How do you get degrees of freedom in this experiment when you're going to look it up in the critical region? The way you get it is you say degrees of freedom equals your sample 1 size minus 1 plus your sample 2 size minus 1, right? And that'll be the sum of the degrees of freedom values for the two samples. Okay, so from there, let's just make sure that we understand all the steps that we go through when we use all this stuff. Remember, the steps are the steps of the hypothesis test. There are the 4 steps that we've been talking about, so let's go over what those 4 steps are right now. Remember, step 1, we've been saying, is where you identify your 2 hypotheses, right? So we have the null hypothesis here. Remember, it's saying that there's no effect. Your sample that you did something to is not going to be any different from the sample that you didn't do anything to. If that's the case, then their population is going to equal the other population, and their difference then will be 0. On the other hand, if there is an effect, right, that is being predicted by the second hypothesis, the alternative hypothesis, which says that the 2 population means are not equal to 0. And if they're not equal to 0, then they're not equal to each other. Okay, so You've identified your two hypotheses. Remember, your step 2 from there is you're going to go find your critical region that's going to be this T value that you're going to get. Remember, the way you do it is you go to the T table, right? That is that sheet there, and you use it to find your critical region using these three numbers, right? Whatever the alpha level is that the researcher gave you, how many tails there are in the experiment, and then what your degrees of freedom are. Remember, the degrees of freedom are this equation that we just talked about. Okay, so then that leads to step 3. Remember, step 3 is where you then go and do your calculations. Remember, the order of calculations is that, well, the last thing that you're going to calculate is T. Remember, to be able to do that, you have to get values that contribute to T, right? The first value you have to get is that standard error. How do you get it? The way that you get it is you go and first calculate your pool variance, right? So we'll say that in terms of step 3 steps, first, you'll go calculate your pool variance. Second, you'll go calculate your estimated standard error. And then third, you'll go calculate T. Remember, and then step 4 is where you make your decision, right? The decision is, are you going to reject the null hypothesis, or are you going to accept the null hypothesis? Remember, the basis is you reject the null hypothesis if this T is bigger than this T. Okay, so let's say that you've done all of that and you found that you did reject the null hypothesis. Your step 3T was bigger than your step 2T. If that were to happen, then the thing that you need to think about is something that we've been mentioning before, the effect size. Right, remember, effect size is if there is a difference between the samples, we want to have a sense of, well, how big was that difference? So we're saying the first thing that's happened is you got a T that in step 3 that was bigger than your T in step 2. That meant that you rejected the null hypothesis. If you rejected the null hypothesis, that meant that the treatment was effective. With that, right, the rule we're going after the effect size is we want to know if the treatment was effective, how effective was it? And that's what effect size gives you, right? It's, how effective can be measurable by asking, well, how big was the difference between the two samples? Okay, so there are two ways that we've talked about calculating effect size. One is Cohen's d, and the second is r squared. But also is this third way that we've been talking about, and that was that confidence interval. I'll go over each one of these individually, right? So I'll start with how to calculate Cohen's d first. All it is the sample mean of group 1 minus the sample mean of group 2. It is over the square root of the pool variance. All of these values will always be given to you, or you'll calculate those, so you'll have them by the time you get to this point where you need to calculate this effect size. Right, and remember, what is that? What is Cohen's d? It is the standard difference between your sample 1 mean and your sample 2 mean. The second type of effect size measurement is r squared. Its formula is where you're going to take the t that you got, right? By the way, this is your step 3 t that you're going to work with here. You're going to take that t that you got in your step 3 and you're going to square it, and that's going to be your numerator. And you're going to divide it by that same t squared, but added to your degrees of freedom, right? Remember, this is the degrees of freedom. That's what you calculated and you used in step 2. Okay, once you've calculated that, then you're going to come up with some decimal value. And that decimal value you'll be able to think of as the percent of variance accounted for by the effect, right? So if there is a difference between the two samples, this percent is like what percent you can say that difference is due to the thing that you did to the participants. Okay, so then the last type of exercise measurement was looking at that confidence interval. Here I'm just defining it again real quick. Remember, so this is where you're estimating the size of the population mean difference between the two populations or treatment conditions. Okay, so what was the formula for this? This is the modified version of the formula, right? I presented the formula first in chapter 9. This is it modified for chapter 10. But remember, the idea here is you're basically solving for this mu information. Chapter 9, the mu information was just a 1 mu. Here in chapter 10, the information that you're talking about is the difference between the mu1 population and the mu2 population, right? But you're going to say that that's going to equal the difference in the two sample means. And then remember, when you got to this part, the plus and the minus, the reason why we got the plus and the minus there is because we were saying that you're going to do these two different kinds of equations. One where you're going to do this all as this part being adding this part to this part. And then another equation where it's going to be this part being where you're subtracting this part from this part. Okay, the other thing you want to remember is how you got that T. That T that you're using is that step 2T that you got, right? So that's that critical region T. And then the last term is the standard error here. This is that standard error that you've just calculated for in your chapter 10. Now remember, the whole idea here is what you're saying with all this is you're saying that if I know what this is, and then given this and this, I'm going to know what this is, right? And that's the whole goal. You want to know what this is given whatever this is. So that we do it is we say, okay, well, I got some kind of distribution here. And in the middle is that in the middle of that distribution is a mean. In this particular case, the mean is that x bar 1 minus that x bar 2. And what you're saying is that if this mean is right here, I can estimate that the population mean is going to be somewhere around that sample mean. And the way that I can estimate it is I can say it's going to be somewhere, right, that population mean is going to be somewhere in this region. Why are we doing the plus and the minus? Remember, the reason why is because the minus equation answer will be what goes here, and the plus equation answer will go what's going to go there. Okay, so that's everything I wanted to say about that part. Before I let you guys go for the set of lecture notes, I do want to just run through one whole problem with you guys, just to make sure that you understand how to do a problem. The way that we're going to do it is we're going to solve the problem by going through all the 4 steps, right? You're going to see what all the 4 steps are going to look like, at least for chapter 10. Okay, so first we'll identify what the problem is. In this example, we're saying that we're running an independent measures t-test, right? So because independent measures, we're saying that we collected 2 samples of participants, a sample A and a sample B. And maybe we did something to one group, but we didn't do something to the other group. Maybe we can go back to that experiment where we're talking about yoga improving classroom behavior, right? Maybe we could say that group A got yoga, group B got no yoga. Remember, the measurement after that was we were saying, okay, well, if they got yoga, then the yoga was going to cause the number of that classroom misbehavior to go down. The way that we were going to measure that was by number of office visits, right? If a student got in trouble, they had to go to the office. Here what we're seeing is then, for this group, this is how many times they had to go to the office after the yoga. And this is the number of times that this group had to go to the office after the no yoga. What you're seeing is that for group 1, their average office visit was 3. For group 2, their average office visit was 6. Right, so what this is suggesting is that group A, I'm noticing I'm calling group 1 down here, so that's group A, that's group B. Right, also notice this is a typo here. In my sheet, the mean for group A was 6. Actually, it's the mean of 3. But what this is saying is that after the yoga, this group had a lower number of office visits. And after not getting any yoga, this group had a higher number of office visits. The question that we're asking here is, okay, well, we got this difference between this sample and this sample. Does that difference mean that the treatment was effective, or is that just a difference that's meaningless? Okay, so how do we go about answering that question? First thing we're going to do is we're going to do our step 1. We're going to state our hypotheses. Remember, we got the 2 hypotheses. The first one is the null hypothesis, which says that there's no effect. The way this one would be written is we'd say the population mean for the first group minus the population mean for the second group is equal to 0. There is no difference between the 2 groups, right? This population got the yoga, but it didn't change them from this population. Because they're still the same, their difference is 0. That means that there's no effect. Okay. The other hypothesis is your hypothesis H sub 1. Right, this is the alternative hypothesis. It says that there is an effect. How are we saying that there is an effect? We're saying there's an effect because this group's difference from this group is something other than 0. If it's something other than 0, that means that there is a difference between the 2. That leads us to our step 2, where we identify that critical region. Remember, we have basically the 3 bits of information, right? You're told what your alpha level is, you're told how many tails you're using, and then you're also having to figure out your degrees of freedom. Remember in the chapter 10, way of doing it is we're saying that we're taking the degrees of freedom for group 1, and we're adding that to the degrees of freedom for group 2. Both groups had an N of 8, so 8 minus 1 plus 8 minus 1 equals 14. So then we go and we look that up at our critical value table, and we find then that our critical value is going to be plus or minus 2.145. Okay, so that leads us to step 3, where we go to compute, right? We go to actually calculate our t statistic. Remember, step 1, the first thing that we do in step 3 is we first calculate our pooled variance. What do we need for a pooled variance? Remember, the formula here is you are taking your sum of squares for the first group plus the sum of squares for the second group. We've got that information up here, right? That's where we're getting that 16. That's where we're getting that 24. And the denominator of this is, remember, degrees of freedom for the first group plus the degrees of freedom for the second group. Both had an N of 8, so each is 8. Each degree of freedom is 7. That leads you to a pooled variance of 2.86. We use that 2.86 to go then calculate our new standard error, right? Remember, now it's that pooled variance in the denominator, or the numerator of both these fractions over the n's, right? That's, we got these 8s here, gives you a standard error of 0.85. Take that standard error of 0.85, we then use it in our t equation. Remember, the t equation is your x bar 1 minus your x bar 2. That's where we're getting this 3 and this 6 here. Remember, the original equation was minus mu 1 minus mu 2. Remember, I said that difference is supposed to equal 0. So actually what you have here is your x bar 1 minus your x bar 2 minus 0 over your standard error, which is 0.85, gives you a negative 3 over 0.85, which gives you a t value of negative 3.53. Remember, now what you're doing is you're comparing this t to this t. And you're asking, is this t bigger than this t? In this case, we're saying that it is. Negative 3.53 is bigger than negative 2.145. Because this is bigger, in step 4, when we go to make a decision, we're going to conclude that we should reject the null hypothesis and we should say that we have a significant effect. Real quick from there, let's just make sure that how will we go to calculate effect size from here? Our Cohen's D would be that sample mean 1 minus the sample mean 2 over your pooled variance, and that gives you a Cohen's D of 1.77. Your R squared value is, remember, you're saying that you've got your T squared, and it's the T that was in your step 3. You're going to square that here, you're going to square it there, and you add to 14, gives you a 12.46 over 12.46 plus 14, and that gives you a R squared value of 0.47. Remember that we'd articulate this, so we'd say that your R squared is where 47% of the variance is explained. Okay, I'm not going to cover the confidence interval effect size here. I'll do that in your odds problems. So we'll end this lecture here. Thank you very much.